We all think we know how to jump, right? I mean, you bend your knees, you push off the ground, and you're in the air. Simple. But what if I told you the real engine behind that powerful leap isn't what you think it is? What if the secret is hidden away, not in the muscles that push, but in a totally different system that acts more like a hydraulic press? Well, today, we're diving deep into the hidden mechanics of the jump. So let's just ask the big question right up front. When you launch yourself into the air, where does that explosive power really come from? Is it your quads, your glutes, the usual suspects? The answer, it turns out, might completely surprise you because it's hidden in a part of the leg we almost never think of as a power source. Okay, so here's the old story versus the new one. The common belief, the one we all kind of learn, is that jumping is all about your big extensor muscles on the front of your thigh, your quads, powerfully shortening to straighten your leg. Makes sense, right? But this fascinating new theory suggests the primary force doesn't come from the front at all. No, it comes from pressure, like actual hydraulic pressure building up in the back of your lower leg. It's a complete 180 on how we think about this movement. Now, to really get why this new theory is so compelling, we first have to look at all the holes in the old one. And it turns out that simple push-off model has left scientists with some really big, really confusing unanswered questions for a long time. Let's start with the math, because the math doesn't lie. To lift an average person about 2 feet off the ground, you need roughly 353 joules of energy. Now, scientists are smart. They can calculate how much energy our muscles and tendons are supposed to provide. But here's the problem. When they add it all up, the numbers just don't match. There's a pretty significant chunk of energy missing. And this is puzzle number 1, the energy deficit. If the power sources we know about, the muscle contractions, the stretchy tendons, if they can't account for how high we can actually jump, there has to be another system at play, some kind of hidden, more efficient source of power that we've just been completely missing. And here's the second puzzle, and honestly, this one's even stranger. It's the timing. You'd think your super powerful calf muscles, right, the ones that feel like the engine, would fire really early to generate all that force. But in study after study, we see this bizarre sequence. The little muscle on the front of your shin fires first, then your thigh muscles. And get this, only after you've pretty much started to leave the ground do your powerful calf muscles hit their peak. Why on earth would the main engine fire so late? It makes no sense. So, how do we solve these puzzles? This missing energy, this weird timing? Well, the answer might lie in a really cool kind of revolutionary new concept that changes everything. It's a force called TIP. TIP. It stands for tube internal pressure. And the idea is that your lower leg isn't just a bunch of muscles pulling on bones. Instead, I want you to think of that deep compartment in your calf, the part wrapped in that tough saran wrap-like tissue. Think of it as a tube. The theory goes that this tube fills with fluid, and when it's squeezed, it generates this immense hydraulic pressure. Like squeezing a tube of toothpaste from the very bottom, all that pressure has to shoot upwards and escape somewhere. So, with this new picture in our heads, this idea of a hydraulic press literally built into our legs, the entire story of a jump completely changes. So let's walk through it step by step, using this new TIP model. You see, a jump isn't just one single explosion. It's a 3-stage process. It all starts with priming the system, or, filling the tube. Then comes this rapid, passive pressurization. And only at the very, very end do the muscles come in to actively amplify that pressure for the big release. Okay, so first up, stage 0. The system just gets primed as fluid naturally pools in that calf tube. Simple enough. Then comes stage 1. As you bend down to get ready for the jump, you naturally stretch your Achilles tendon. And this stretch acts like a clamp, mechanically squeezing that now full compartment. And since fluid can't really be compressed, the internal pressure just skyrockets. And this is all happening before you've even tried to fire a major muscle. And this leads us to the final stage, which is just brilliant. Now that the pressure is already super high, the calf muscles fire. But here's the key. They don't fire to shorten and pull on anything. No, they contract isometrically, which just means they stay the same length, to simply amplify and contain that immense pressure. That pressure finds the path of least resistance, which is straight up, shooting out from behind your knee and rocketing your thigh bone and your whole body into the air. So this is the crucial point, and it's captured perfectly in this quote from the original research. Knee extension is a result that appears. Think about that.
You're not actively thinking, okay, straighten my leg, using your quads. In this TIP model, the forceful release of all that built-up pressure causes your need to straighten. It's an effect, not the cause of you going up.
Now, this system is incredibly efficient. It's beautiful, really. But what happens when it breaks down? Well, this new model also gives us a really compelling explanation for a feeling we've all had. Losing your spring or your pop when you get really tired. It's called the fatigue patch hypothesis, and the idea is pretty simple. When your muscles get fatigued, they don't get tired uniformly all at once. Instead, you develop these little patches of contracted fibers right next to patches of relaxed fibers. It creates this uneven, kind of messy situation inside the compartment. And just look at this comparison. When you're fresh, the tip system is dominant, the pressure is contained, it shoots straight up, and you get this huge power output with very little energy wasted. But when you're fatigued, those patches make the whole compartment leaky. The pressure can't build up properly. The system fails. And you're forced to switch back to that old, inefficient method of just muscling through it with your extensors, which results in low power and a ton of wasted energy.
So let's bring all this together. This one single, elegant theory doesn't just give us a new way to jump, it actually goes back and solves all those old puzzles we started with. And it really gives us a whole new way to think about how we move.
Remember that missing energy? Well, TIP is so efficient it completely closes that gap. And that totally weird firing order of the muscles? It's not weird anymore. It's the perfect sequence to fill, passively load, and then actively amplify the pressure. And here's a cool bonus. This high internal pressure might even help protect our joints by gently pushing them apart during high-impact movements.
So, what's the big takeaway here? How can you actually use this? Well, it's about shifting how you think about the movement. Instead of a violent muscular push, think of it in 3 stages. First, fill the system. Do a minute or 2 of just light calf pumps. Second, smoothly load your 4 feet to build that pressure up nice and evenly. And finally, release. Think less about pushing off and more about a quick, tight squeeze of the calves to let all that built-up pressure launch you into the air.
And this brings us to one final, fascinating question. The jump is one of our most studied human movements, and it looks like we may have had the core mechanics wrong this entire time. And that just makes you wonder, what else? What other simple, fundamental movements that we do every single day might we be completely, totally misunderstanding?